सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै।
Earlier we had seen how to write a test bench. Now prior to starting simulation, we will just see how the design flows for VLSI circuits in general. To start with, you had to have what is called preliminary specifications, and prior to this you would have done market survey or what you call market research, and then talk to various customers or users, and then identify a product as such. And having identified the product, you are now in a position to formulate very preliminary specifications as such. And once you had done this, you may be requiring more inputs as such as you progress along this detailed specifications, working out of that. And during this course, you need to interact with the user and ascertain whether you are proceeding in the right direction or not, and accordingly amend your specs, and then come to this, wherein once you are through with this iteration as such, you come either through this path or through this path, implying that you have finished with all collection of inputs as such. Once you are through with the inputs, it is now time for drawing out a very detailed specification as such. You should also put a block diagram of the whole scheme, both including hardware as well as software as such. And once you have done this exercise, this may also be an iterative process with the user, and ultimately a time will come when it is time for you to freeze the specifications. This is exceedingly important because from prior experience I have seen that people keep on changing the specs even towards the end, and you are in for trouble as such. Therefore, it is very important that you freeze the specs right at the incipient stage, and only then go along with further steps, because you may also have to do the hardware. So it may be easy for you to amend your Verilog code, etc. All software aspects you can do it quite easily and rapidly. But hardware, once you have done and halfway through making a PCB, etc., it may be very difficult for you to retract, and hence the need emphasis for freezing the specs. So then you get the user concurrence and then go on to the next step as such. So this is entrant for this particular slide. And once you are through with the detailed specifications, both hardware as well as software, you may have to prove your concept. You might have developed a new algorithm or a new architecture you are attempting. So all these are still unproven. And in order to prove that, you need to go for a higher level language such as C or MATLAB, and then code it in one of these or both if you wish, and finally test it with all possible combinations and IO combinations that you may be encountering later on in the actual design when you do the implement the hardware as such. So once this is through and you are sure that your concept is working, and you can even get user feedback even at this stage, although it's not shown. And then it is ripe time for you to start the hardware design as such. And you start on the architecture here, and while designing this architecture, you should keep in mind the hardware aspects as to how you are going to implement. Are you going to put a register and a pipeline register, and all that consideration you have to do here. And mind you, as I have said earlier, you tend to design this hardware architecture also in the same way that you have coded in C or MATLAB. So this approach is entirely different from this. That you should bear in mind very clearly. You should not start coding in the way that you code C, right? And this is what we have already seen, such as RTL coding is what is implied here. And that is naturally the next step here. So once the architecture is through, you start identifying different blocks and start coding, and it should conform to RTL techniques as such. And next step is you use now the simulator, let us say, or for that matter even in synthesis tool you have a compiler, and so also in synthesis, simulation tool. And this step is you compile your Verilog code, both the test bench as well as the design as such. And once there are no compiling errors, you can go on to next stage, which is simulation. And if you encounter errors, naturally you have to fix those and go back to compile. And then this is an iterative process, and beginners especially will have frustrating experience in this to start with. They may encounter hundreds of compiler errors. You have to wade through these errors, and once you are through with this, then you will be at home later on. So we'll see some of the we'll take some exercises practically, so that what type of errors can come, and try to resolve that as far as possible. And this is the only bottleneck in the, in the entire design, I should say, especially for a beginner. And once you have set on that, this will be very rare, and maybe one or two, and which you will be able to fix very little effort and time. And so once you are free of errors, so it is time for you to go to simulation. In simulation, as we have already mentioned before, it is nothing but a timing diagram that you get here. So it is any signal will be displayed in terms of different times. You can choose microsecond or nanosecond as the case may be. And today we are going to see on the simulation aspect. So after we are through this design flow. And here also you will be encountering lots of bugs in your program, in the sense that it doesn't meet the functionality that you had really designed it for. And so if there are such bugs, once again you have to identify which part of the code is erroneous and then correct the same, and then go back to square one again. So we'll keep repeating, coming back to this compiling time and again. Right. This is the whole design process is an iterative process. You have to do it number of times till you get a totally error-free or bug-free code that will work on your IC finally. So if there are no bugs, naturally go to the next step, C. So this step is the synthesis. I forgot to tell one more thing. There are so many simulators available in the market, which we'll be using model sim as such. I think it is 5.5D, and version I don't remember. We can look into that. And so next step is synthesis as such. And regarding the simulation, there are other simulated tool also. See, for example, if you are designing an ASIC, simulation tool will be a DC compiler of Synopsys, if it is ASIC design as such. And there are many other simulated tools also. And similarly, next step is synthesis. The synthesis step, what you do is you map onto a particular target device. For example, if your end target is an FPGA, field programmable gate arrays, then you need a tool, and the tool that we have here and we will be seeing and using will be Simplify as such. It's from Simplicity Corporation, whereas the simulator tool is from Mentor Graphics. And so there's Leonardo Spectrum also available, another synthesis tool as such. And in the ASIC platform, it will be once again that DC compiler which we have already seen in Synopsys. And so once you fix, if you encounter errors here also, here the type of errors that may get in is there may be you might have given frequency of operation to be a very high value, and what could be achieved on a particular target FPGA is not able to match to, that speed you have specified. So it may also give compiler error and setup hold time violation. In a way it will give this, and finally it will do the optimization of your logic. That's what the tool is. So it's in essence it is optimization of logic as well as to provide you an EDF file, what is called electronic data information format, it's called. It finally gives that EDF for short with an extension of .edf. So that will be the file that it will create finally, which you can take into the next stage, what is called place and route. And here once again, if there are errors, you have to again go back to compiling and do the whole iteration once again till you are totally free and it has allowed you to go to the next step. And so in this step, what you do is, here it has created EDF file as such, and you will invoke what is called vendor specific platform for place and routing. So what is place and route is, here in synthesis you will get gate level netlist as such. For example, FPGA will be using what is called lookup tables, MUX, and the like of it. All basic primitives pertaining to a particular FPGA as such, or a group of FPGAs will have similar such primitive gates or MUX and so on. So in terms of that, synthesis tool will give in the EDF file netlist as such, and that will be the input for place and route on particular platform. For example, you go for Xilinx FPGA, so you need to have place and route of Xilinx. So also for say Altera, another alternate FPGA vendor, and so on. There are so many other vendors, so Actel and some Lucents and so on. And once you are here, what it does is it places different primitives, gates, muxes, etc. What we have already seen at strategic points. It locates the optimum point, possible point, and it also you can also put your specify your IO pins, etc. And finally it starts routing it. Routing is just having placed different components inside. It starts interconnection. That's what you call here, and this is a time-consuming process. Maybe it may take an hour or even more. I have seen even 72 hours running on place and route, and so also the synthesis tool, right? And large files will invariably take a very long time, but most of the small files which we have already dealt with, it's a question of 5 minutes or 10 minutes, not more. And so here, what you have, as I mentioned before, IO pins can also be assigned as such by the user, that is you as a designer. So, and these are all what we call constraints. And then you need speed of operation, and that also is specified not only in synthesis, and that information is also conveyed into this, and it will take that as a constraint, or you can even override that constraint, and you can run with the constraints. So it's basically for in FPGA as such, these constraints will be basically speed of operation, and it's basically a speed of operation as such, and along with the pins that you want to configure as. And in ASIC here the constraints will be in addition to this you will have a power also, power as well as area, chip area as such, that also will be available as a constraint that you can program. And once again you will encounter different errors or limitations which will be reported if it is that is if the constraints are not met, such as let us say frequency of operation you have specified for a particular FPGA as 100 megahertz, but it has reported that it is able to give only 60 megahertz. So what you have to do is if you take 60 megahertz for your design, that's no problem. Even then I think you will have to get rid of warnings etc. Till you when you go to the next step, and otherwise you can if you want 100 mega, if you are particular about 100 megahertz operation, then you will have to go correct the identify where you can introduce additional pipelines etc. so as to improve the speed of operation, and then for all that you need to correct your code. So once again you have to go all the way right up to that B compiling, right? And if it is merely constraints that is of the speed, you don't have to go there, and you can straight away tone it down to lower frequency that you want and then proceed here. Are you following it? Is it clear? So next step is here in this previous thing, this is the route adapted for FPGA design. If it is ASIC design, you branch off, you bypass this route and take from this straight away to the next. And previous FPGA final stage was F, whereas if it is ASIC, you go to this. So otherwise there are so many common factors there, so approaches and blocks, you have to go through the exactly the same thing except for this small deviation. And here in FPGA this is entry point after the place and route, and here right up the after the place and route it will give you what is called bit stream, that is dot bit extension of your design file, and that is the one which you will be selling if you are an IP core designer basically. If you don't have to do anything other than just deliver the bit file, and most probably you don't deliver the source files. It all depends upon the contract that you have with your customer or user. And so now next step is what you have to do is so far we have concerned ourselves with only the simulation and mapping it onto the device on FPGA, and that is not adequate, because what is the guarantee after doing all this exercise that it will work? So you have to do what is called back annotation. This will update all the gate level delays etc., incorporate all that, and there are set of commands for this, and running which you get a back annotated file, and this will be again once again a .v file. You started with a .v file and out comes a .v file, but the file size will be enormous. If you go through the .v files, it may be very difficult for you to recognize your own design. And that is the reason being this reflects the actual device, gate primitives that we have already seen before, such as mux etc., LUTs, right? All those will be appearing in this .v extension file, and this will have timing also. So there is another file called SDF, that's a standard delay format. This also these files, another group of files are required, which we will see when we go into the details of that. So only then it can do the back annotation. Back annotation is the one which reflects the actual gate delays. So having got this, once again you have to go to step B and then do the compilation and simulation, right? So here there will be most probably there will be no compiling error, but unless you compile you cannot simulate, right? So you have to load etc. So you enter the model sim for simulation once again. So you can straight away go to model sim and do the compilation right there and simulate here. So here will there be any problem associated? most probably functionality is okay, but you don't know whether timing has been really met. You have let us say you are simulating still at 100 megahertz, whereas the previous tools, say Xilinx also gives a revised estimate of the frequency of operation, and that is the final. Synthesis tool also gives that one. That is rather a rough estimate only. It doesn't actually reflect the true thing. Only the vendor specific software will reflect, and that is place and route of Xilinx, which we have seen earlier. And here, if this timing is too close and if it is slow, then you will have timing problems. So if it is okay, then what you do is you go on to the FPGA implementation. Otherwise, you have to go back to compiling once again and wait through the entire design cycle that you have done earlier till you are totally free of all timing problems, right? And as I mentioned before, the whole thing is just iteration till you settle down onto final target as such. So when all errors are fixed into Toto, then what you can do is go on to the hardware implementation of the FPGA. You can, this development tool that we have can program, let us say, E2PROM or EPROM, in which your bit stream will reside. And finally, you will have to make a hardware PCB, and then with this particular target FPGA that you have already designed using the whole design flow as such, and then you had to evolve a strategy for testing the PCB along with this, and after that you can integrate with this development system that we have, say that of Xilinx, and you can download your bit stream right onto the FPGA that is housed on the PCB that you have made. And so you have this basically is a software path, we can say, and parallel to this, right from the inception when you have frozen the specification, you should also start the hardware work. For example, you should know FPGA, you can at will you can with some few exceptions you can change the IO pins, as we have seen before, because user constraints you can specify the IO pins as such. So once you have given a particular, you can write in the beginning stages, you can go about freezing even the hardware, saying that FPGA, these are all the IO pins, these are all the clock signals, and based on that information, PCB work could have started right from day one when you started the Verilog coding as such. So that means to say hardware and software design goes hand in glove, and you had to interact with each other. Normally a team of engineers will be allocated for the hardware design, another team for the software coding, say this Verilog coding, and you had to interact with each other and get the final product. So that's all that are implied here. In addition to that, you have even mechanical design, another group will be evidently doing it. So that's the final get-up, that's what you see apparently. So, and you have to take the ergonomics also into account while making a product, and all that are implied in this. And so is the case with ASIC implementation. Whether you have your code residing ultimately on an FPGA or an ASIC, what we have just now seen regarding the hardware is the same fundamentally. And in this case, we saw that after a synthesis tool, see here you may be using Synopsys DC compiler for synthesis tool. Once you have these iterations are all primarily the same. So once you have fixed all errors, it will come through this path and into this. So next thing what you have to do is the actual chip layout. So a chip is a very complicated affair, and you have to have a look at the layout, and for this we have a tool called Cadence in the ASIC domain. And another alternative is the Synopsys DC compiler itself will give you, you can have your own constraints, some TCL files, etc., and it will give a database file. You can feed that database file straight away to the ASIC vendor as such, and then he'll take care of layout as well as layout verification, and he may finally give you back-connected thing, because we don't have that right here as such, and many people may not have this. So there is no problem because we can, ASIC vendor himself will support this. So no matter whether you do it using your tools such as Cadence here and finally do a layout verification, finally you will end up in making the ASIC, and you have to hook up the hardware as we have seen before in this case. This explains the design flow for both FPGA as well as ASIC as such. And then before you start on a particular design as such, you have to have a strategy for or a methodology for designing. See, for example, you may be doing a very complex design. Yeah. See, if you take FPGA platform, there may be some, if it is Altera, I think they have some LPM modules. If you take Xilinx, they have Core Gen, right? They are all vendor specific. So if you had coded on vendor specific tools, and then you are you can't naturally use it in ASIC flow. So my approach, what you have already seen here, it is friendly for FPGA platform as well as ASIC platform, so long as you stick on to that style of coding. So it is, so to say, an universal way. So we'll try to stick on to that particular thing. So as far as possible, avoid vendor specific standard modules, I mean their own modules. So coming back to this design methodology, and you have what is called a top level design module. In the examples that we have already seen, say combinational sequential circuit design, or even in a small design that we have considered, we had a design file, I said. So that design file is the only file as such. There are no down the line sub-modules, right? So that you can identify that module as the top level module. If you have a bigger design, it is a good practice to downsize it to smaller sub-modules and further sub-modules in this fashion, and it can go any number down below. So the idea is that we manage only small thing at a time. So once you have tested a small module, then you can put them together and then test the higher module, right? So another method is this top level top down design methodology means you have this, you start with the top level module, and here it will have something like an ordinary IC with different IOs specified. So take that one and merely call whatever submodule you want, you merely make a call of that, and assuming that those submodules are already available to you. So you can, in that case, you can start from the top and go down, and where you have not done, you don't have a module there, a missing one or only partially available, which you had used for some other project, you can take that, make an amendment or write it afresh, and then go down here. So like this you can go step by step into different modules and keep on developing those modules. At every stage, naturally, you need to have a good practice will be to have a test bench for every module as such, whether it is this module or this or any other module or even intermediate. So if you have a test bench, you can rest assured that it will work right on the top when you integrate all the modules as such. So this methodology wherein you start from the top and then go downstream is called the top-down design methodology. In contrast to this, you can even make an approach in the reverse manner. For example, you have already done a couple of projects, let us say, and you have used different lower modules such as adder, multiplier, subtractor, and floating point, and so on. So they may be readily usable. So they may be residing at this level, and you can start going in the reverse direction and putting these modules together, and you can make a little more higher level thing, which will give a particular functionality for intermediate application as such. So like this you can create all these lower modules and go move up in this case, and then finally do the top level thing. And we can't say which is the best approach, and many people prefer this approach. What is actually popular and what I have been following is a mix of both these methodologies. So sometimes I may have to start here and also start from top to bottom. So there may be a meeting point in between. So we can't just pin it down that this is superior to the other. So let's now go to simulation. We'll use model sim. See, this version is SC 5.5D. I wonder whether you can read on the TV screen. Anyway, that's what is here. I hope you can see this M. So we'll just double click this in order to open the model sim. You see two windows opened. Now the first thing that we have to do is, we have what is called a create a project, then open a project. If you want to create a new project, so you use this one. That's what we are going to do now. If you enter the same project afresh another time, so you will use open project and enter. If you want to see online documentation, you can use this here. I think you need internet connection for this connection for this. And next time you want to go straight away to proceed to model sim, you can use this, proceed to model sim. You can have either that way or this way also. If it is going to be the very same project that you had done before in the last session, you can straight away use proceed to model sim. We will now just start with the creation of a new project. We just click, and you see here there are two windows, and what you have here is a project name you have to give here. This is corresponding to the create project that we saw in this menu as such, and you see here a project location. So where exactly your design files are residing, it's good practice to go there, and then in order to do that, you have a browse. Another window pops up, and here it is there in this directory. So user, then RAM, then VLSI design, then etc. That is it, right? So, and there's nothing more there. So we'll just go here. We'll say open, and the whole thing has come over here. And now you have to give a project name, meaningful name. Now what we will do is, we'll take that simple design that we had seen earlier, that is a 2 input AND gate design. So that the name is AND underscore 2i. So we'll give that itself as a project name. And there is one more thing called, we have a library here. This one you have to create a work directory, and you have to work in that one, not in IEEE. Otherwise some platform dependent files will be overwritten. That's not a desirable thing. So you use always a work directory as such. Just say OK. Let us see what is happening. So here that window is closed. Now you have this may be difficult for you to read, and okay, I'll just enlarge this. Okay, even then it will be very difficult for you to read. If you want to know what directory you are in, you can just say pwd in this command mode. This is a model sim with greater than symbol. This is just a prompt for the command. So if you say that one, note that we created change the directory to this up to etc. That is what is in now. So now if you want to see what files are there in this directory, you can just say dir. It lists all the files. Now let us see whether we have that and2in.v and its corresponding test. This is a test bench for that. So we have this here. Now next step is, what we have to do is, we have what is called project and library. You click on the library so that work is used here, right? And now what you have to do is do the compilation. So design compile we have given, and then it menu popped up. In that it lists .v files here. So you can just see here all .v files are used here. And now what we want is, we had a test bench as well as a design, and if we remember that we have already included design file in the test bench. So it is enough if you just compile this test. It will automatically go to this design and do the compilation. You don't have to do it afresh as such. So if you just double click this here or single click, it will appear here, and then use compile. Had you double clicked, it would have started the compiler straight away. That will be a shortcut for you, you can adopt later on. Now let us see, compiler had run, but it appears on this window. So what, you see that there are no errors, if you see here. So I'll read it out for you. It says compile module and underscore 2in. This is the design file, and then same file with underscore test extension for the compilation of the test module as such. A test bench is also compiled here. So it always starts with the design lower module and then moves higher up here. And the top level module also just gives a just shows it. That's all. So once you have done the compilation, you are done with it. So it just said done. So next step is you have now compiled your test bench as well as the design. Now it is high time that you load it into the simulator. So our aim is to see the timing diagram as such, and we will be seeing that shortly. So before that, what we have to do is load the design that you have compiled. So again use design, and you down before after compile you see a load design. Just click on this. The whole thing is menu driven. You have only to just note what I have been saying for different things, and we may be summarizing all these comments later on. And okay, now what we want is the test bench here, and you don't have to invoke this here because this is the topmost module here. So if you double click, this will appear here, and this will be energized. This is a load button here. So I am just double clicking this, or okay, double click this. So it says work dot undin underscore test. So this is the top level module that we have for the test bench, and it is in that work directory. So now you can load this file. Now let us see what happens when we load here. So you just watch this here. Okay, I'll just load. While loading the design, we just now encountered an error. I traced it to the system time being different here. So it's right now it has been set to correct time as such, and now there's no error while loading the design. Anyway, I'll repeat this for your sake. And design, then you will say load design. Then you have this is the top test bench. So double click on this and load. So now you see there's no error, but some warning is given. This is a trivial warning. You can ignore. What it says is module and 2in does not have a time scale directive in effect, but previous modules do. The previous module is the test bench that has a time scale we have already given, but not mentioned in the design as such. That's what is mentioned here. And notice that as mentioned before, we should be free from technology dependence. So there must be no time element in the design. That is the reason why I did not put a time scale there, but only on test bench, because that is a vital thing for while testing it on the simulator. And so next step is we will be eagerly waiting to see the waveforms, how your design works as such. So that's what we are going to see here. So you have, after design, there is one view here. Just click on view, and if you see different signals, you will have same signals by name, and just click on this. So it opens out a window which lists all the signals that you have in your design. So A, in, out are all the design, and in this you have again file, edit, view and window. This may be difficult for you to read out, and yet just follow my words. And I am going to click on view here, and what it says is, again it has 2-3 options here, wave, list, log, filter and so on. So in this, go to wave and then take your cursor in this fashion, then go down. We want all the signals in the design, including the test bench, not only your design but also the test bench, all the signals. So if you use this one option, you will get all those. I am just clicking on signals in design. So immediately you see a waveform window opened. Just make it wide enough for looking at the waveform. Now what you have is this is and underscore to in underscore test. All of them are same, except that these three signals pertain to the design. First signal is A, then in. I'm sorry, this is test bench, not design. So and in and then out. You remember we had used in the test bench in and out instead of B and Y, and those are design. And U1 is the instantiation we had used earlier while instantiating in the test bench, and we call the design module as U1. So now the signals here are listing for the design here. So A, B and Y. This A correspond to very same A, and after we run we had to see that A, B and Y are exactly the same as A in and out, right? Although this pertains to the design module and this pertains to the test bench. Now another thing is unfortunately on your TV monitor you may not be in a position to read out this. That's why I am reading out every time here. And if the waveforms are displayed in this fashion, it may be too crowded for you. So fortunately you have one way out of this, and that is what is called format. Just click on the format. Now nothing happens because all are de-energized. So we should first make a run, then we'll see format. So what we'll have to do now is we have to run your test bench. So then you will get there is you can see different one is called restart here, one button, and run here, then continue to run, then run all, run minus all. So you click on this one, then it will run through your test bench for all the choice. The truth table was just 2 input corresponding to that 4 states were there of the truth table. That's what you are going to see here. So it has given now, upon clicking you saw that it has given a waveform here, and all of them seems to be flat. In a minute we will get everything working together. So and also you see it had run through your test bench, that is sources and underscore to in underscore test, and having run through the test bench, once again it will be difficult for you to read this here, and I'll open another file with bigger fonts. So finally it has stopped at $finish because it has finished the thing. Since we don't require this source file, we can as well close it here. And similarly, if you don't want that, signals also can be closed, but let's not worry about it. So now what we'll do is we say here there's a time axis here. Right at this point it is 100 nanosecond. So this is not the correct range. Let us see whether we can shorten it further. Right now you see waveform appearing here. So another you can use plus to zoom out, in, and to zoom out you can use minus here. It happens 2 times every time, I think. And this also you have you can shift here. You can go to any part of the waveform as such. And another thing is we had I think 80 nanosecond or so, and for that we have one more here. There's one lens here. It says zoom area. If you want to zoom a particular area, let us say from here, you can just press zoom area, and there's a cursor in plus mode. So if you just say this, it will zoom to that. Now suppose you want the entire 80 nanoseconds, you just press this here. The entire say it was 100 nanoseconds perhaps, so it has given the entire waveform. And there's also a cursor here, and now what before that these waveforms are very crowded. So what we'll do is we'll change this here. I just used shift and clicked on the first signal and last signal. It has highlighted the whole thing, and what we will do is we need to increase the spacing, right? So in order to increase the spacing, we'll say format, then height. So it is 17 pixels it's marked here. So I'll make it as 90 pixels. Let us see what and then say apply, and it has then say OK. Now you can see the waveform here, and I can as well blow it out. Now you are able to see the waveform, complete waveform for entire say 100 nanosecond. Now let us see the functionality. So if you just click somewhere here, all the highlighted signals will go. You can go to any signal here, and now let us see the functionality as such. See, we have here, if I put the cursor, I can put the cursor anywhere, here, 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 and so on. So if you see our, let us see, we have, we'll open the test bench here. What it says here is, we are applying at 0 point of time, 0, 0, then 0, 1, 1, 0, 1, 1, and for which we need the AND output as such. So let us see once again here the waveform that you have. So are you able to see the waveform clearly there, at least now? I hope so. Okay, we had to live with it, right? So there's no way, that's why I'm reading it out. So let us see, this is on the design, test bench as such, A, in and out. This is A waveform, and here it is 0 nanosecond here, and 20 nanosecond is marked here, 40 here, 60, 80, and so on. So we said, as per the test bench, every 20 nanosecond we are changing the inputs. For example, right at 0 point of time, we have 0, 0. You can just see here, this is 0 here for A, and for in it is 0. Similarly, for A and B also, you can see that as 0 here. And if you want this, this is called symbolic representation. If you want, you can have it in binary also. You can just say format, then radix, then say binary. And okay, I didn't mark, right from here, you just mark all this. Click here, and then with a shift you click here, then all will be highlighted. Then you say format, radix, and then you say binary. So it has changed here, instead of ST0 it is now 0, so implying that the whole thing is in binary. So if you want in decimal, you can have, you can select right from here. See, all decimal, octal, unsigned, hexadecimal are all there, and symbolic is the one which was there as the default. So we'll see more of this later on. So now coming to this, we see that 0, 0 is the applied input. You can see the waveform. I'm sure you can see whether it is low or high. Can you see this low and high there? That, so thereby you can recognize. Now this point is 20 nanosecond. So it is 0 here and 0 here. You can also read it out here. The truth table, every step of the truth table you can read it out straight here. And its output also is listed right here. For 0, 0, ANDing operation is 0. So you get a 0 here. Here also you can see pictorially. We have already seen earlier timing diagram. What you have here is precisely the same timing diagram. And suppose you go for 20 nanoseconds here, just click the cursor here. It is 0, 1 as the input here. And once again A and B are also 0, 1. So this proves that test bench and design are basically the same signal. As far as same signal is concerned, you can see the waveform right here. And here, suppose you want to locate this B closer to in, you can just hold the mouse button and then drag it here. So it has located now B. So you can compare the two waveforms and see whether they are same. I'll revert it back here once again. So now we have seen tested for 0, 0 condition. For 0, 1 condition, this is 0, 1 here, right? So it is high now, this is 0. So it is 0, 1 condition. What should be the, if you AND these two, you should still get 0, that is what is here, and it shows 0 here. And similarly for the next, at 40 nanosecond, we are again changing here. So that is now 1 and 0 applied now. The stimulus applied is 1 and 0 for A and in. And that's what you have high here and low here. And for this, naturally, you have to have again 0, right? And the last one is 1, 1. This corresponds to 1, 1 here, and corresponding output must be 1 here. That's what you see here. So this confirms that your design is working. In other words, the functionality is fully tested. And mind you, there is no gate delays, etc. involved right here. That can come only with the place and route, which we will be doing in future. And Another point I would like to mention here is, you just notice here I have commented out the earlier thing that I had mentioned. One of you asked a question whether this 20-20-20 can be put in a different way to reflect straight away the actual timing. Yes, we experimented with it, and we arrived at another thing that is listed here. That is what is actually working. What you have seen just now is that which is working. So I didn't run the earlier thing with same 20 nanoseconds appearing. Here you can see 20, 40, 60 and so on. So, but here the advantage is that you can straight whatever you put, you get right at the same time. But the disadvantage is you have to put for every signal as such. Once again here, so you have to pay a price for that. So you have advantage as well as disadvantage. Another disadvantage in this approach is, so in sequential circuit we will be seeing we want to initiate data at a specific time prior to the clock striking. So it was shown as 25 nanosecond. So in earlier case adopted it was this actually, and this approach here at 25 nanoseconds I had put a data there. So that means once you put that one, automatically all are relative. So all are offset by the same amount. But that is not the case here in this particular example. So it is not offset, but the actual time itself. So that is another disadvantage here. So the designer is at, free to choose one of these two depending upon the need, circumstance, etc. And another point I would like to mention is, there is one more here. We have also seen 100 picosecond appearing in 1 nanosecond time scale as such. That is the resolution we have said. So if you see, if you uncomment this one and comment the other things, and then this will come into force, in which case we can see that this 0.3 has also taken into effect, right? This we will see next later on. Thank you.